Okay, so what we have here is we have a video that is really aimed at, I've called it grade 9 skills. This is the skills that I feel could come up that really are differentiating between grade 7, grade 8 and grade 9. So we're going to start with vector diagrams. A typical question that you could be given is that use a scale diagram. Please do not use Pythagoras or trigonometry when it says a scale diagram to determine the resultant force acting on an object that has a 10 Newton force acting south and an 8 Newton force acting east. So if I was in the exam and I did this, I would actually just up in the corner, I'd draw a little diagram of what's going on. I'd say, okay, there's 10 Newton force acting south, there's an 8 Newton force acting to the east, so this is my scenario. Okay. Now what a lot of people then do is they say, okay, well what I can do is I can work out the resultant force, because I can say, well, if that's 10 and that's 8, I can join that up. But the issue with doing that is the direction is totally wrong. This resultant force direction that you've got is just totally wrong. Think about it. If you are pulled in this direction and then you're pulled in that direction, you're going to go somewhere in the middle of those two forces. That's going to be the direction of the resultant force. So let's have a think about how we do this via a scale diagram. First of all, you need a scale, and I've got a scale there of 1 centimetre equals 1 Newton. And then you need to use something called the head-to-toe method. So the way in which you do it is you get your point, you put your point somewhere, and you draw one of the forces just as normal. So I've chosen to draw the 10 Newton orange force downwards. So I draw the 10 Newton force downwards. Now previously what I've done up here is then I've got the 8 Newton force and I've drawn it back at the object. But you don't do that, you use something called the head-to-toe method. What you do is you draw the 8 Newton force from the head of the 10 Newton force. And you can see that's exactly what I've done here. We call it the head-to-toe method because the toe of the 8 Newton force is at the head of the 10 Newton force. So when I draw that 8 Newton force on, I then join the object where the 10 Newton force started with the end of the 8 Newton force, and that will be my resultant force in the correct direction. So to find your resultant force, which has magnitude and direction because it's a vector, you use a ruler to find how the distance of this resultant force, the length of this resultant force. Let's say it's 12 centimetres, and using my scale it's going to be 12 newtons. You then need to work out the direction. The way in which you do this is you do this quantitatively with a protractor. You measure an angle and you say, right, that was 30 degrees from vertical or 60 degrees from horizontal. So that's the first skill that I feel could come up that could be a good distinguisher between those top grades. The next one is the equation that's given to you, and even though it's given to you, it's often one that causes quite a bit of confusion. So v squared equals u squared plus 2as, or v squared minus u squared equals 2as. Let's just go through it. V is final velocity, u is initial velocity, a is acceleration, and s is displacement or distance. You can only use this equation when an object is constantly accelerating, and the best example I've got of that is an object that's falling. An object that's falling is constantly accelerating at g equals 9.8 meters per second squared. So have a look. The orange ball, here's the question. The orange ball falls from rest due to gravity for 10 meters. Calculate the final velocity of the ball. So s is distance, and we can see them from the question, it travels 10 meters. U is initial velocity. Well, it's from rest, and a little tip I've got is that most objects are from rest, so u is going to be 0. Not all, but most. V is final velocity. Well, final velocity is exactly what we're trying to find out. And then a is acceleration, which we know is due to gravity, which is 9.8 newtons per kilogram. Remember, you don't need to remember that, you're going to be given it. So I need to use my my equation, and that's v squared equals u squared plus 2as. So then I need to square root both sides. That's v is the square root of u squared plus 2as. I then substitute my numbers in. So v is 0 squared, so nothing, plus 2 times 9.8 times 10. And then when you plug that in, you calculate correctly, you get v as being 14 meters per second. Now it's well worth being able to rearrange all of these variables in this equation to make them the subject. So have a look here. V is the square root of u squared plus 2as. A is v squared minus u squared equals 2as. S is v squared minus u squared equals 2 over 2a. And u is the square root of v squared minus 2as. Okay, so make sure you're able to rearrange all of those into the correct forms. Another grade 9 skill that is often really badly written in textbooks is Newton's third law of motion. And Newton's third law of motion, even in your textbooks or revision guides, is that every action has an equal and opposite reaction. Now, looking at the mark schemes and looking at this new GCSE, that's not specific enough and is not fit for purpose. Here's what's in your spec, which I don't think is terribly helpful. It says, when two objects interact, the forces they exert on each other are equal and opposite. Now that's absolutely fine, but the template that they've actually used in mark schemes and what I'd like you to use from now on is this, that the force from object A on object B is equal and opposite to the force from object B on object A. So the scenario that they want you to talk about Newton's third law for, just pick out the two objects in there. Here's an example, just focus on this part over here. Here we've got a pink box, and that pink box is resting stationary on a table. So using my template, we can say the force from the box on the table is equal and opposite to the force from the table on the box. That is the exact reason why the box does not start falling through the table, and is the reason why the box does not start magically levitating away. I know and I remember that there was a past exam question that you guys sat as a PPE, which was to do with a bike and a trailer, and it asked you how Newton's third law related to the bike and the trailer. And all you need to put is use my template. The force from the bike on the trailer is equal and opposite to the force from the trailer on the bike. Just remember over here, Newton's laws of motion, so we've got the third law of motion as we've been through. The second law of motion is F equals ma, an equation. The resultant force is mass times acceleration. And the first law of motion, Newton's first law of motion, is that an object will continue at rest or at a constant velocity unless acted on by a resultant force. The final key skill is on momentum. Now we know momentum is mass times velocity. You need to remember that equation, and hopefully you do. Hopefully you also remember the conservation of momentum. It's a bit like energy. It states that the total momentum before an event for all objects is equal to the total momentum after an event for all objects. Events mostly being collisions, but it could be explosions. An example of this in action quantitatively is this. It states that here we have a ball A and a ball B, and ball A is moving at 2 meters per second initially, and ball B is not moving at all. Ball A has a mass of 2 kilograms and ball B has a mass of 3 kilograms. So what you do is you calculate the total momentum of both of those objects, add them together to get the total momentum before the collision. So we have the mass, which is 2, times the initial velocity, which is 2, because momentum is mass times velocity, and 2 times 2 is 4. The momentum of B before the collision is the mass 3 times 0, well 3 times 0 is 0. So the total momentum before the collision is just the momentum of A, which is 2 times 2, which is 4 kilograms meters per second. Kilograms meters per second. Then we go on to the second part of this diagram, and what we're actually trying to find out here is VB. We're trying to find out, well, what is the final velocity of our ball B? And all we know is that the velocity of A is 0.7 meters per second, and we already knew the mass of A is 2 kilograms. So if the total momentum after the collision must be 4, because of the conservation of momentum, we can set it up nicely. We can say the mass of A times the velocity of A, the momentum of A, is, plus the momentum of B, plus the mass of B, plus the velocity of B, the momentum of B. So the momentum of A and the momentum of B added together must equal 4. So here we can see 2, the mass of A, times V, the new speed of A. 2 times 0.7 is 1.4, plus 3, the mass of B, times the new velocity of B, 3VB. And we know that momentum of A plus the momentum of B equals 4. So then we set it up. 2 times 0.7 is 1.4, plus 3VB is 4 kilograms meters per second. So then we minus 1.4 from both sides, so 3VB equals 2.6. And then divide both sides by 3, and that therefore means that VB will equal 0.87 meters per second. Now, just one last thing. Let's make sure that we can do this qualitatively with words as well. So if we're going to do it with words, we just need to see, well, just look at A on their own and B on their own. A has not gone down in mass, so mass has stayed the same, but the velocity has gone down, so therefore the momentum of A has gone down. Now let's go with B. Well, B, its velocity has gone up because it was 0 and now it's 0.87 meters per second. The object B's momentum has gone up. And then what we can do to summarize all of this is we can say that the total momentum before this event is equal to the total momentum after an event.